We are next going to look at a probability distribution known as the chi-square probability distribution. This particular probability distribution has a number of uses, and the one that we will be focusing on much of the time in our course is with respect to it comes up when sampling is being done and you're computing then S squared, the sample variance. So this is what the chi-square PDF looks like. Let me get my red pen out here. It's defined for possible values of y greater than 0 for a continuous random variable y. F of y is equal to this quantity right here. And of course, if y is then less than 0, it's f of y is equal to 0. Now, inside this particular probability distribution, there's the Greek letter nu, as in nu. This is a particular parameter of this particular distribution. And as we've seen in the past with other probability distributions, these parameters they do control the shape of what the distribution looks like. And we'll see more on that shortly. But hopefully this probability distribution function looks a little bit familiar to you, because actually it's a special case of another probability distribution, the gamma probability distribution. So the corresponding expected value of y, it happens to be nu. The variance of y happens to be 2 times nu. And this all comes about with the relationship with the gamma probability distribution. So because of that, we are not going to formally prove it. Now, this nu, again, it's the Greek letter nu. This nu has a special name. It's called the degrees of freedom. You'll see this name pop up in a number of different probability distributions when you're dealing with some kind of sample. At the end of this notes, I will talk about what degrees of freedom means, but for now, let's just simply call it degrees of freedom. The chi-square part there, the chi corresponds to a Greek letter as well, and so because of that, you will often see people write out chi-square as simply the Greek letter chi and then a superscript 2. Now, with this particular probability distribution, we will often be wanting to get quantiles with it. And so there is actually a nice little shortcut way of actually denoting in a symbolic manner a particular quantile from this distribution. You'll see similar notation like this now for the rest of our course. And the shortcut notation is this: chi-square, and then in the subscript, alpha, comma, nu. Nu, again, corresponds to that degrees of freedom parameter. That's going to control the shape of the probability distribution. The alpha corresponds to the area on the right-hand side of the distribution to the right of the quantile. So in other words, this chi-square sub alpha nu is the 1 minus alpha quantile from a chi-square distribution with nu degrees of freedom. So here's kind of a crude diagram that shows what's going on. This alpha here is typically going to be a small number, maybe like 0.05. And so the area to the right of this quantile is 0.05. The area to the left is 0.95. And we want to know, well, what quantile from this chi-square distribution gives us that value? A way to symbolically denote that is with this corresponding notation. So thus, the probability of random variable y with a chi-square distribution with nu degrees of freedom, that probability of y being less than this quantile is 1 minus alpha. Oops, and that should be, oops, let me redraw that. It should just be alpha right there. Okay, so to help you visualize this probability distribution and understand the quantiles associated with it, I developed a simple Excel file that's somewhat interactive so that you can examine this further. So I've drawn this chi-square distribution shown on the plot. This is the blue curve to scale. And you're going to see some lines dropping down from the chi-square distribution going down to f of y equals 0. That corresponds to the location of the quantile. So for example, the 0.95 quantile from a chi-square distribution with 10 degrees of freedom is 18.30. So if you see where my mouse is here, look at the green line here. This is the location where that quantile would be. The area to the left of it is 0.95. The area underneath the curve to the right of it is 0.05. And as you might imagine then, if I look at then the 0.99 quantile, meaning area to the right of it is 0.01, we would get a greater value for that quantile. It's 23.21, and we can see where that falls underneath the curve here as well. This file is set up again so it can be somewhat interactive. So if I change the degrees of freedom to 20, we can see the plot change as well, and all the quantiles are updated. So this is just a quick little Excel file that I put together to help you understand what this notation, what a chi-square distribution looks like. Now we might be interested in finding probabilities and quantiles from this chi-square distribution using R. How can we do that? First of all, just to make sure you see this, if I want to find the probability that y is less than 3.84, that would be equivalent to finding the CDF evaluated at 3.84 for this particular probability distribution. And let's suppose that my degrees of freedom nu is equal to 1. And so to find that probability, I just need to find the integral of 0 to 3.84, my f of y dy, as we've done many times before with other probability distributions. In R, we can greatly simplify the process here by using the p chi-sq function to find that, where the first argument is q, that quantile, 3.84, and then instead of saying nu, R uses df for degrees of freedom. You'll see people, including I did in that including I did in that Excel file, people often just use df for degrees of freedom corresponding to this nu. To find the 1 minus alpha quantile from a chi-square distribution, again what that means, the 1 minus alpha quantile, excuse me. What that means is we need to solve this integral here for c, set it equal to 1 minus alpha. So if alpha was 0.05, we can now use the q chi-sq function to find the quantile, where the probability to the left of it is 1 minus alpha, and say we have the same degrees of freedom as before. To find the height of the curve, in other words, to find the actual f of y value itself, we can use the d chi-sq function. And so, like we've done with other probability distributions, I've used the curve function to actually plot it. And here's what the chi-square distribution looks like with only 1 degree of freedom. And you can see that this is severely right-skewed. In fact, the chi-square distribution will always be right-skewed. We saw that the right skewness before with the degrees of freedom of 10 and 20. And so that's a 2-scale drawing of this particular probability distribution. And here's the probability distribution again with 10 degrees of freedom, like what we saw in the Excel file. Now, to find these quantiles, to find the corresponding probabilities, some books, I would say most introductory textbooks in statistics, will still often have a table similar to what we saw with the normal distribution table. They'll have a table to help you find these corresponding probabilities or these quantiles. There's really no reason to use those tables anymore, so that's why I decided not to even introduce it here. Simply, we can go to R and use the correct functions. Okay, so let's talk about why we are interested in this chi-square distribution. And that is, we are interested in the probability distribution for S squared, our sample variance. So we've seen this before. It's S squared is equal to the sum I equal 1 to n. I'll write it in the random variable format here. Y sub I minus y bar squared over n minus 1. This will vary from sample to sample to sample. So it would be nice if we could quantify that amount of variability through a probability distribution function. Now, since S squared comes about through sampling, people will often refer to what we're going to be doing right now as finding the sampling distribution for S squared. So, in order to find the sampling distribution, at least the way that we're going to approach it in our class, we have this random sample, y1 through yn, from a population, but we do need to say that the probability distribution that characterizes that population is a normal distribution. There are other ways to approach the sampling distribution for S-squared without having that. Typically in introductory course, though, we just focus on this one particular case. If you are interested in knowing more about this other case, let me know. Now, this normal distribution, every random variable corresponding to it has a mean of mu, variance of sigma squared. And so with this assumption, then, we can form a quantity, let's call it chi-squared for the lack of a better name, where we take n minus 1 times s squared, divide by sigma squared. And this has a chi-square distribution to it with n minus 1 degrees of freedom. Again, n is our sample size. So notice the role that n is going to have in the shape of this probability distribution. It's obviously a very important role. Now, sometimes also you will see people represent this quantity a slightly different way, where they write out what s squared actually is. It's the sum of yi minus y bar squared over n minus 1. And notice what happens here. This n minus 1 cancels out with that n minus 1, and then we're left with this quantity here. In the end, I ended up bringing the sigma squared inside the sum, and you don't have to, but I ended up doing that here. So then what does this result mean for us? Well, what this says is that we have a way to look at probabilities associated with what particular values of s squared can be. This is going to be very useful to us actually in the next section once we start talking about inference from a sample to a population. In terms of the limitations relative in comparison to what we have with the central limit theorem, obviously we have that underlying normal distribution assumption. However, at least the way that we're going to use this probability distribution in our class, we're going to see that even if I have violations of this assumption, how we end up using this chi-square distribution will still work out rather well for us. Next, we're going to talk about unbiased estimators, and we're going to apply the idea of an unbiased estimator to s squared. So in general, an unbiased estimator is a statistic with an expected value equal to the corresponding parameters trying to estimate. So if we had some statistic, let's just call it t for the lack of a better way to denote it, and let's say t estimates theta. If the expected value of t is equal to theta, then we can say t is an unbiased estimator. We've already seen one unbiased estimator, and that was y bar. Remember that the expected value of y bar is equal to mu. And so as you would imagine then is for a statistic to be an unbiased estimator, that's a very desirable property. We would like this statistic on average if we were to take a sample, calculate, take a sample, calculate again, take a sample and calculate again, and average all those values of those observed statistics. We would like that observed value, we would like that average value to be very, very similar to the parameter that we're trying to estimate. So it's really, really desirable to have an unbiased estimator. And for this s squared, that is an unbiased estimator of sigma squared. Let's actually go through a formal proof to show that. Now, to do this proof, we're going to go back and use some results that we've had in the past. And that is, remember, if we had two random variables, x and y, with constants a and b, we know that the expected value of a times x plus b times y is the a times expected value of x plus b times expected value of y. So the key thing here is that we can always bring an expectation within a sum or a minus as well if we had that instead. And we can always factor out constants from that expected value. Also, what we've seen before is that the variance of a random variable y can be rewritten as the expected value of y squared minus expected value of y, that quantity squared. But what we have not seen before is that what one could do is just simply rewrite this equation using some algebra. Let me do some erasing. Suppose we move this expected value of y squared over to the right, to the left side. And so what we're left with then is that the expected value of y squared is now the variance of y plus expected value of y squared. Also, what we've seen is that expected value of y bar is equal to mu. And what we've seen is the variance of y bar is equal to sigma squared divided by n. Now, one could also rewrite the variance of y bar similar to what I did with that second bullet. It's equal to the expected value of y bar squared minus the expected value of y bar, that quantity squared. And so by doing that, then again, we can bring this part over to this side, just using some algebra. And we can say then that the expected value of y bar squared is equal to sigma squared plus expected value of y bar, that quantity squared. Okay, with that, then we're going to use those results in this proof. Now, this proof looks pretty long, but I really went step by step through this proof to help you out. So it's a lot longer than what it probably needs to be. So let's say, just to make sure we're following this, y1 through yn is our random variables, and each of them have an expected value of mu, and each of them has a variance of sigma squared. Then here's our expected value of s squared. Based upon what we saw before, we know we can always factor out a constant from that expected value. So let's call that step 1. Step 2 here, what we're going to do is simply multiply out the stuff that's inside this sum. So yi minus y bar squared is then yi squared minus 2yi y bar plus y bar squared. Next, what we can do is move this sum through this little part here. So now I have the sum of yi squares. And then I have minus 2 times y bar times the sum of the yi's plus the sum of y bar squared. Now you might be wondering, how can I do this with the y bar? And just to make sure that is clear, let's take a look at a case such as this. Suppose I have the sum of the yi's. Okay? That, of course, is y1 plus down to yn. Suppose I put another summation out here as well. So I have a double summation. Okay? Now, notice in the summation here, there's no I anymore because we've already written it all out, all the terms. And so what this is saying is that I want y1 plus yn. That's for I equal 1. Then I also want y1 down to yn. That's for I equal 2. Plus, I can keep on going again, y1 plus yn. This is for I equal n. So in other words, what I have here, I have n different y1s throughyn's summed. Or in other words, n times the sum I equal 1 to n of yi. Okay, so then if I did something like this, the sum I equal 1 to n of y bar, we get essentially the same result. N times y bar. This y bar essentially is a constant for this sum because it's already been, the stuff that's inside that y bar has already been summed over. And so because of that, then, I can bring this y bar outside that sum. Now, if that's still confusing, what I recommend that you do for this, or in fact any parts of this proof here, is suppose n is equal to 2 and write everything out, remove all the sums, and you'll see in fact why this actually occurs. Okay, so step 3, I move that sum through. Then step 4 here, I have the sum of the y bars squared. Well, we just saw that the sum of the y bars is n times y bar. Same thing happens here, so I have n y bar squared. Let's go to step 5. Whereas what we've seen is that we can move expectations through sums of random variables. So that's what I'm going to do here. I'm going to move my expectation through. So I have an expectation here now, one here, and one here. Then for step 6 here, I'm going to take a look at this right here. Now, y bar is equal to the sum of yi, I equal 1 to n over n. And if I wanted to, I can move this n over to that side so that now I have n times y bar is equal to the sum of the y sub i's. And that's exactly what I did here. Here's my n, and I have an extra y bar there now. So y bar squared. And so that's step 6. Step 7. I have a constant inside the expectation, so I can move that on the outside. And then look what we have here. We have 2 times n times expected value y bar squared plus n times expected value y bar squared. So we see that they both have exactly the same thing there. So I can simplify, and in step 8, I have now just minus n times expected value y bar squared left. Okay. Page down a little bit here. Once again, I can bring the expectation side of sums, sum of random variables. So now I have the expected value y sub I squared there. And then, so that's step 9. And for step 10, what we're going to do is apply, let me do a little bit of erasing here. We're going to apply this result that we had here. The expected value of y squared is equal to the variance of y plus expected value of y quantity squared. And also, expected value of y bar squared is equal to the variance of y bar plus expected value of y bar squared. So that's what I did. I replaced these two terms and wrote them out in terms of the variance and the expected value. Well, what are these expected values? What are these variances? Well, we can also call the expected value of y sub I equal to mu. Okay, so that's what I did there. Also, I should say the expected value of y bar also is mu. The variance, and that should be no square there. The variance of y sub I, that's just sigma squared for every possible y sub I. Also, the variance of y bar is sigma squared divided by n. Okay, so that's step 11. Step 12, let's focus right here. We're going to simplify. I have an n here, and I have an n in there, and there. They cancel. I have just a negative sigma squared left over after I move the negative n through. Also, now I have a negative n mu squared. Over here, for this particular sum, I'm taking the sum of sigma squared in different times. What is that? N times sigma squared. Take the sum of mu squared n different times. What is that? N mu squared. And so look what happens. This cancels with that. I can factor out a sigma squared. Put that out there. And then I'm left with an n minus 1 inside the brackets. That n minus 1 cancels out with the 1 over n minus 1 that I had out in front. And voila. I have sigma squared. So in the end, the expected value of s squared is equal to sigma squared. Thus, now we know why, when we form s squared, why we divide the sum of the yi minus y bar squares, why we divide by n minus 1 rather than n only. It's so that we can get an unbiased estimator of sigma squared. So lastly then, let's end with, well, what are exactly degrees of freedom? Excuse me. Here's a simple way to think about it. Suppose I have 3 numbers, and I happen to know the sum of them is 6. Well, if one were to give you 2 of those 3 numbers, and this sum you could figure out what that third number is. So because of that, what we would say is the degrees of freedom would be 2. In other words, let's say the sum of these numbers is 6. If I picked one number to be 1, picked another number to be 2, then I don't have a choice for what that last number would be. It has to be 3. And so therefore, my degrees of freedom are 2. Now, why is this important? Well, this was for a sum. Of course, with y bar, it's primarily based upon a sum. So y bar actually has a degrees of freedom of n minus 1 if I had a sample size of n. And in a similar manner, s squared has a corresponding degrees of freedom of n minus 1 as well. So with that then, we can see now with these probability distributions, people who have developed them have built in then the corresponding degrees of freedom into the probability distribution, and then that degrees of freedom then is going to control the shape of them. So there's a real brief introduction to what degrees of freedom are. So with that then that concludes in this section on the chi-square probability distribution.